Self-supervised learning is incredibly important in both language and vision, but the way these two domains learn is fundamentally different. In vision, self-supervised learning is usually used to train an encoder. We design a task like teacher-student distillation, contrastive learning, or mask prediction, and the goal is to learn good representations. After that, we freeze or fine-tune the encoder and train a separate downstream model, often a shallow classifier. So, representation learning and task learning happen in two stages. Language models work very differently. Language models are almost always trained using autoregressive objectives. The model predicts the next token step by step, and by doing this, it directly learns the data distribution itself. There is no separate downstream model. The same model that is trained is the one we use at the inference time. Representation learning and generation are unified. This raises a natural question. Can we bring this autoregressive learning paradigm into the vision domain? The answer is yes. And one such approach is called Next Embedding Predictive Autoregression, or NEPA. Instead of predicting pixels, which is the main weakness of traditional generative vision models, NEPA operates entirely in latent space. An image is first split into patches. Each patch is then mapped to a latent embedding using a shallow convolutional network. These embeddings form a sequence very similar to tokens in a language. A transformer is then trained to predict next embedding autoregressively. At each step, the model only sees past embeddings and predicts what comes next. This is enforced using causal attention, just like in language models. The key idea here is that we are not predicting pixels. We are predicting embeddings. This avoids modeling unnecessary low-level texture and noise and instead focuses on higher-level structure and semantics. To make this work at scale, the authors introduce several architectural refinements to the transformer network. They apply QK normalization to stabilize attention. They use Swig-glue activation in the feed-forward layers for better expressivity. And they use layer normalization without learnable parameters combined with learnable layer scaling, which improves training stability.